Okay, thank you. Good morning, everyone. So let me begin where I left off. So where I left off was about describing the geometry of the affine Grassmannian slices, or the definition even of the affine Grassmannian slices. So let me just quickly review where I started, the last 5 minutes from last time, and then we'll continue. So just recall that what we had here, we picked a reductive group G, like for example, you can think of GLM. Then we considered this quotient. Well, either version, there were two versions, and so you can think maybe most intuitively maps from C star into G divided by maps from C into G. And another geometric way of thinking about the affine Grassmannian is to think of it as modifications of the trivial principal G bundle. So a pair consisting of a principal G bundle and phi. And what's phi? It's an isomorphism between P and the trivial, which is the trivial principal G bundle on P1 minus 0. When G is GLM, you have two other ways of thinking about the affine Grassmannian. Well, for one thing, you can think of instead of principal G bundle, you can think of rank M vector bundle. So you have a modification of the trivial rank M vector bundle in P1. Or you can think in this lattice way. So then you can think the affine Grassmannian instead of lattices, CT lattices and CT T inverse M. Okay. Then we saw there was these special points in the affine Grassmannian coming from coheights of G. So maps from C star into the maximal torus of G gives you a point in the affine Grassmannian. We took the orbit through this point, and we got what we called spherical Schubert cell, a finite dimensional, not usually projective because I didn't take the closure, a finite dimensional quasi-projective variety called Gur lambda. Then we have the following example of GLM. So if we take GLM, such a lambda is just a sequence of integers. I had this condition about being dominant. That means that the sequence of integers is decreasing. And then just for convenience, I also demand that the last integer be positive. This element t to the lambda, or t to the mu in the affine Grassmannian, will be represented by a matrix. This will be a diagonal matrix with these different powers of t along the diagonal. And this orbit, Gur lambda, can be described in the lattice model as those lattices that are contained inside of this standard lattice, and moreover, that the quotient is isomorphic as a CT module to this standard direct sum here. If you prefer vector bundles, you can say we have a vector bundle, rank M vector bundle, which is embedded as a subsheaf of the trivial rank M vector bundle. So this is an inclusion not of vector bundles, but inclusion of coherent sheaves, such that the quotient is supported at the point 0 and is isomorphic to, well, the coherent sheaf defined by this mess here. Okay, so that was Gur lambdas. Then we had needed these opposite things called W mu's, which will be finite codimensional orbits. And they're going to be orbits of a different group, which is going to be this G1 T inverse. So it's the kernel of this evaluation homomorphism, sending T inverse to 0. And these guys are a set of kind of Schubert cells that are transverse to the Gur lambdas. Then we formed the intersection of Gur lambda bar with W mu, and we called it W lambda mu. And we saw, well, I didn't really explain why, but I claimed that these were affine Poisson varieties. So let's look at GLM now. So remember principal G bundle, same as rank M vector bundle. So W mu is a set of pairs, V phi, where V is the rank M vector bundle. Phi is this trivialization away from 0 as before. And now where does the mu enter the game? So mu enters the game as a condition on the vector bundle. So recall the theorem that every vector bundle on P1 is a direct sum of line bundles. And line bundles of P1 are just O of n, or O of k for some k. So every rank M vector bundle can be written as a direct sum of O of some mu1 up to mu m. And so this mu exactly tells us the isomorphism class of this vector bundle. So vector V is a vector bundle which is isomorphic to this O of mu1 up to O of mu m. Actually, there's one small additional condition. which I'll sort of suppress under the rug. But this vector bundle acquires a special flag called the in general, a partial flag called the Harder-Narasimha flag. Actually, it's not unrelated to what Pierre was talking about. And there's an additional condition that's somehow related to the fact that I took the kernel here, which is that this Harder-Narasimha flag in infinity under this isomorphism coincides with the standard flag. But, okay.
May I ask you a question before you move on?
Yeah.
So I imagine that eventually you would say that these W, lambda, mu are somehow symplectic dual to Nakajima equivalent or something.
The W lambda mu, yeah.
So in the case in which instead of taking principal bundles over P1, we take principal bundles over a surface. I know that there are some people that generalize this affine Riemannian for surfaces and so on. Is there a similar symplectic duality feature enters in the, has someone studied this? Is expected from
yeah, that's a very good question. So Dinakar is more of an expert than me, but yeah, so there's a work of Braverman and Finkelberg who studied what you're suggesting, so considering the case of surfaces and trying to define kind of analogs of this thing for surfaces, and which will be like kind of an affine Grassmannian slice, but for the affine Lie algebra. And yes, it's expected that those will be symplectic duals to the Nakajima equivarieties associated to the affine Dynkin diagram. And on the other hand, via the Coulomb branch construction, you can also produce a kind of symplectic dual. And I believe that it's known in type A that those things coincide, and in other types it's not completely known that they coincide. Dinakar, you agree with me about that assessment? Yeah. So it's expected that but it's not, even though Braverman and Finkelberg worked on both sides of that thing, they somehow have not matched it up.
These are the same that Vezzossi is constructing with the collaborators, because Gabriele Vezzossi has two papers about something similar, in which he fixes some flag, so you can fix a surface, and then you say that they are isomorphic outside a point or outside a curve, and then you have a surface, a curve, and a point, and then some other conditions, so you're not aware of.
I'm not aware of it. The version that Braverman and Finkelberg studied is more like a surface and a curve. Okay. Well, actually, it was specifically like P1 cross P1 with a P1 at infinity, or something like that. So, yeah, I know. So I don't know, but it sounds, well, it sounds plausible. Okay. Any other questions? Okay, so so this guy is an affine variety, and now we'd like to make a symplectic resolution of this W lambda mu, or at least a resolution, which will turn out to be a symplectic resolution. So how do we do that? We do that by what's called the convolution construction. So suppose I have lambda, and I write it as a sum of dominant weights, lambda 1 up to lambda n. Then I can form this convolution construction on the left, which can be defined kind of in a group theoretic way, like I defined the affine Grassmannian originally, or it's slightly simpler just to write it in this principal bundle way. So you can think of it as a sequence of these principal bundles. This first one is the trivial principal bundle, and then we have some other principal bundles. I have these phi i's, which as before are isomorphisms between each pair away from the point 0. And there's a condition on the poles of each of these phi j's, the poles at 0, because this phi j is isomorphism away from 0, so it has potentially some poles at 0. And there's a condition on its poles, which is dictated by this lambda j, and it's called the Hecke type, which is equivalent to what I was saying before about this g of gt orbits. Okay, and it'll be very important for us, the following thing, which is that there's a special subset of these lambdas which are particularly nice, which are called the minuscule ones. And when lambda is minuscule, ger lambda and ger lambda bar coincide. So typically, you can take the closure of this ger lambda, you get some union of smaller ger mu's, but sometimes ger lambda is already closed. And this happens when lambda is minuscule. So these minuscules are a subset of the fundamentals. So for example, in SLM, all the fundamentals are minuscules, and so they look like this. They're usually written omega k, and a bunch of 1s and then a bunch of 0s. And in this case of GLM or SLM, the corresponding Gur lambda is just a usual finite dimensional Grassmannian GKN. And this minuscule condition is useful because it's exactly the condition that allows us to make a resolution. So if we have lambda written as a sum of minuscules, then forming this convolution variety gives us a resolution of Gur lambda bar. So it's analogous in the finite dimensional flag variety situation to making a resolution of a Schubert variety as a Bott-Samuelson variety. So for those familiar with that construction, this is analogous in this setting of the affine Grassmannian. And so this guy will be a resolution if all of these lambda j's are minuscule. And when that condition holds, we can then simply take the fiber product with the W mu, and we obtain a resolution of this W lambda mu. So this guy is a affine Poisson variety, and this guy turns out will be symplectic, smooth, and this map here is a symplectic resolution. So everything we wanted from the beginning of the talk. Okay, I put up a few examples here. So maybe the first and most basic example is if we take the group to be GLM, and we take m times the first fundamental weight, so the same m, it wasn't a typo. In this case, the affine guy will be the nilpotent cone of SLM, and this resolution will be the usual resolution, the cotangent bundle of the flag variety. And we can make lots of other examples. I put this because there were some questions about it from last time. For example, if we keep the same lambda, m omega 1, but change our mu, and necessarily for this to be non-empty, this mu will happen to be a partition of M. And when we do that, we get a slow-to-a slice, more precisely a slow-to-a slice intersect nilpotent cone. And the other kind of like obvious way we can modify this example is change the lambda. So change lambda from being m omega 1 to being any partition of M. And we can similarly look at W lambda mu, and W lambda mu is happens to be isomorphic to a nilpotent orbit closure. Maybe I should write isomorphic here. These kinds of isomorphisms have something called Mirkovich-Vibornov isomorphism. Well, especially the first one. Maybe the second one was already known to Lustig or other people. So in this way, we can see that slow-to-a slices, nilpotent orbit closures, and therefore their resolutions as well, if we were to work with this version here, are all examples of these W lambda mu's. I mean, I should say in type A. This is always a type A story. Outside of type A, slow-to-a slices or nilpotent orbit closures won't usually be of this form, W lambda mu. Any questions? Yeah? So, you're right. No, I mean, typically, so the question is what happens if lambda cannot be written as a sum of minuscules? And typically then this thing won't have a symplectic resolution. In fact, there's exact if and only if statement that we proved in our paper about 10 years ago. It's slightly more subtle than what I just said, but there is an if and only if statement that this is the only possible way to make a symplectic resolution, it turns out. So when you can't write it this way, you can't make a symplectic resolution. Yeah?
What is the Grassmannian or acceleration of fiber product?
Sorry, say that again?
What is the Grassmannian pair over which we're taking the fiber?
Oh, so this is this affine Grassmannian. So this W mu is a subvariety of the affine Grassmannian. So this W mu is a subset of the affine Grassmannian. This Gur lambda with the underline maps to Gur lambda bar, which is a subset of the affine Grassmannian. And I'm taking the fiber product over the affine Grassmannian. Yeah?
Could you say the Gaussian resolution of the map is defined?
Yeah, so in this version of it, of the story, is just a map which remembers just PM and the composition of all the phi's. So this thing maps to Gur lambda bar. I guess I said that below. And the map maps such a thing to PM And the composition, I guess I want, I don't know why these maps are going the opposite way as they were before, but anyway, whatever. Okay, let me just write the composition like this. It doesn't match quite the notation, but anyway. The composition of those phi's. In this language, well, I don't know. It's worth writing it, but you can think about it. In this language, this will be kind of some kind of multiplication. If you write this convolution in the usual way, it becomes a multiplication. Any other questions? Maybe one further comment. Maybe I won't bother writing it, but I said at the beginning that when we had a symplectic resolution, we wanted to have this conical C-star action, and we wanted to have Hamiltonian torus action. And we have those structures here. The conical C-star action comes by loop rotation, which means in this moduli description, it comes from the action of C-star on P1, or in this like group theoretic description, comes from the action on the variable T. So that's going to be our conical action. And our Hamiltonian torus action is going to be the torus of the group G, which is just going to act, well, G acts on everything, on all these varieties, and so this torus will also act. Sorry, G doesn't act on W mu. The torus will act on W mu and on all these varieties. Okay, so we have those two tori that we wanted as well. And now I'm bringing to this theorem here. So there is this Coulomb branch construction, which, as I said, I have not defined. And Dineker, I think, will discuss it at some point in his sessions. Maybe not today, but in the second session. And so there is a way of, from a quiver gauge theory, which just means I just looked at that group, which was the product of those GLs and that big vector space, HOMs, blah, blah, blah. There's a way from that data of cooking up a space called the Coulomb branch. And one reason why you should believe that W lambda mu is a good object to study is because it is the Coulomb branch of that quiver gauge theory. So this was proven by Braverman, Finkelberg, and Nakajima in the simply laced case. And Nakajima and Weeks extended the theory of Coulomb branches to allow to formulate and prove this theorem in the non-simply laced case. Any questions about that? Yeah? Sorry, say that again? Yeah, so remember, okay, it's basically coming. Let's put it over here, pretty much right here. I'll answer your question now. So let's just recap, and then we'll see your answer to your question. So let's recap. So let's say we start with, just for simplicity, let's take simply laced. So we start with a simply laced semi-simple group. We start with lambda and mu, these dominant co-weights. How do we get the quiver gauge theory? It's basically your question. We write lambda as a sum of fundamentals. In fact, we're going to do it in two ways. Two decompositions, which are basically the same decomposition, just written slightly differently. In one way, I write as a sum of fundamentals with some coefficients, omega I. And secondly, I also write as lambda 1 to lambda n, where those lambda j's are, each of them are minuscule, and therefore they're each fundamental. Okay? And I also write lambda minus mu as a sum of vi alpha I, where alpha I are the simple roots or co-roots. And if you can't do this with vi positive, then these varieties are just empty, so it's not interesting. And then the quiver gauge theory, the group of the quiver gauge theory will be, well, or the quiver will be the quiver of G, and the gauge, it'll be as before. I put V's in my what's called gauge vertices, and I put my W's in the framing. So that's how the W and mu determine the quiver, and therefore determine the quiver gauge theory. So the group of the quiver gauge theory is the product of the GLs and the V's, and this underlying vector space is the Hom space of all this arrows here. And so starting from this data, I can form the quiver variety, which I call M lambda mu. So I'm changing notation a little bit from M VW now to M lambda mu. And so that's this projective GIT quotient that I talked about last time. It maps to this affine GIT quotient. So that's my one symplectic resolution coming from quiver varieties. Or I take my affine Grassmannian slice, W, lambda, mu, lambda underline. So I use this lambdas to produce that convolution variety. And that maps to this affine guy, W lambda mu. So I have my two symplectic resolutions coming from the same data. And then, did I answer the question then? Yeah. And then the last thing I want to point out before going on is, well, there's this whole package of symplectic duality, which I'm generally not going to talk about in this week. You can look at the notes from 2021, for example. But one aspect of symplectic duality I want to emphasize is that at least if I take the cohomology of these two symplectic resolutions, they'll be isomorphic. So at least isomorphic in some abstract sense as vector spaces. So these isomorphs are not quite canonical, and we'll get back to that a little later, what we can say more canonically. But as vector spaces, both of these cohomologies are isomorphic to the following thing. So what's here? So these lambdas were co-weights, dominant co-weights of G. Now there's this other group floating around called the Langlands dual group G check. And especially since we're in the simply laced case, you can just imagine G check and G are the same thing. There's no harm in that. But if you're familiar with Langlands duality, then you probably already know what this means. But in any case, the basic point is that a dominant co-weight of G will give us a dominant weight of G check. And so I can consider these irreducible representations of G check with highest weights lambda 1 up to lambda n. So these are these V lambda 1 to V lambda m. I can form their tensor product. And then this sub mu means I take the mu weight space in the tensor product. So it's a weight space in this tensor product of irreps of G check. And in this weight space in this tensor product, so it's a very natural object from the viewpoint of representation theory, can be identified with both cohomologies of both of my varieties. On the one hand, by work of Nakajima, which we'll discuss soon, it can be identified with the cohomology of the Nakajima quiver variety. And on the other hand, by geometric Sutake, which we'll also discuss a bit more soon, it can be identified with the cohomology of this W lambda mu. So I have these two symplectic resolutions depending on the same data, and they have sort of the same cohomology, at least as a vector space. This isomorphism doesn't preserve the grading, and there's like a lot more you can say about this isomorphism, but I'm not going to get into it now. Any other question? Yeah?
So if you take G to non-simple should be the replacement of n.
That's a good question. I don't think there's a completely satisfactory answer to that question. There is a work in the past 10 years by Geis, Leclerc, and Schroer, where they studied a version of pre-projective algebras in the non-simply laced case. But there's not a completely satisfactory version of quiver varieties in the non-simply laced case, as far as I know.
So here, now in the middle when G is simply laced should be to play the role of the expression.
Yeah.
And by claiming that above observe that W lambda mu is the proof branch for any G, so it should be the X branch for non-simple laced.
No. I don't have any other answer to give you besides the one I just gave. I don't think there's a completely satisfactory answer. I mean, in the formulation of this theorem in the non-simply laced case, there's this theory of Coulomb branch with symmetrizers developed by Nakajima and Weeks, but there's not, I guess, a theory of Higgs branch with symmetrizers. So, another question? Yeah. Say that again? Oh, ring structure. Yeah, ring structure is not compatible. Yeah. Oh, the affine GIT quotient. So rather than taking the projective GIT quotient, just the spec of the invariant functions, that will produce you this singular affine variety, Poisson variety. Yes, with some caveats. Yes. let me say. I mean, there's some like more sophisticated versions of this kind of isomorphism and cohomology which work for, which are more, hold more generally, but even, okay, anyway, let me not get into it. Okay. Okay, let's go on to quantum cohomology. Yeah?
Can we get, so these cases, W lambda mu are not necessarily in academical writing, but sometimes they are?
Yeah, so another fact which I didn't mention, which you're entirely correct, when G is equal to SLM, every one of these W lambda mu, or those resolutions, are Nakajima equivarieties. But when G is not SLM, they're almost never Nakajima equivarieties. Yeah. Yeah.
Is this isomorphism of cohomology like equivariant in any way?
It's sort of, but this isomorphism is not very canonical, so you could just pick it to be G-check equivariant. We'll come to some more canonical versions of this a little later. Okay. Quantum cohomology. So we're here at this conference on enumerative geometry, but I'm not an enumerative geometer. So I'm going to talk about quantum cohomology, but I'm not even going to define quantum cohomology. So you'll have to ask somebody who's more of an expert. But let me just briefly discuss some features of quantum cohomology. So we're going to be interested in quantum cohomology of our conical symplectic resolutions. So like those Cour varieties or those Afan-Grassmannian slices. And what is quantum cohomology? Well, it's a ring structure, let's say approximately. It's a ring structure on the cohomology. So a new ring structure on cohomology. And it's defined using 3-point Gromov-Witten invariants. Okay. So a way of like sort of deforming the ring structure which uses these Gromov-Witten invariants. Okay. So as I said, I'm not going to define it, but let me explain some special features of quantum cohomology that in the case of conical symplectic resolutions. So the first special feature is that we need to always work with equivariant cohomology. Well, remember there's these two things around. This, remember, is this Hamiltonian torus, and this is the conical torus, conical C star. And actually, the second one is the only essential one. So this one is essential. We have to work with that because otherwise there's no quantum corrections. Otherwise, the quantum cohomology becomes trivial. And the reason for it, if I understand correctly, is that a conical symplectic resolution emits a deformation to an affine variety. And that deformation is not C star equivariant. But that deformation, if you ignore the C star equivariance, then that deformation would kill this quantum multiplication. And the second special feature maybe is, I don't know, maybe more surprising or something. I don't know. So usual quantum cohomology is defined over a power series ring. So you'll see some expressions if you look at the definition of quantum cohomology, which look something like that. So you sum over some effective curve classes. You have this formal variables q to the beta. And this is going to be an infinite sum. And so you have to work over this power series ring. But for symplectic resolutions, these infinite sums can be, well, at least conjecturally, can be turned into rational functions. And rather than working over this power series ring, we can work over a certain ring of rational functions, which will turn out to be functions on this space here. So I'll come to this part in a little bit. Okay, so that's like, I don't know, second feature. Okay, so more precisely, let me explain the following conjecture of Okunkov. It's a long conjecture. It goes on and on. Okay. Yeah?
You mentioned that for symplectic resolutions, one necessarily should take C star equivalent cohomology, but I know that, but why?
So again, as far as I understand, the explanation is as follows. So because there's a great theory of deformations of symplectic resolutions. They're classified by H2. And part of the theory tells us that every symplectic resolution admits a deformation to an affine variety. So for example, the cotangent bundle of G mod B emits a deformation to I guess to G mod T, to a semi-simple, regular semi-simple or conjugacy class in the Lie algebra. And because of this deformation, I guess, and the fact that the quantum cohomology is invariant on deformation, you could use this deformation to prove that the quantum cohomology is trivial. Unless you work C star covariantly, in which case you're like prevented from doing that deformation, and so so that's why you have the C star covariance. Okay, it'll be manifest in 1 second. Okay, so here's this like conjectural picture of Okounkov describing the structure. So the first part is very interesting even. So there exists a finite subset called the set of Kähler roots. Okay, so it's a subset where of H2. So a subset of curved classes. So a subset of H2. And for each one of these Kähler roots, there's a certain operator on the cohomology. So remember, we're always working in equivariant cohomology, so it's an operator acting on the cohomology, such that, okay, let me just jump to the punchline, then we'll back up 1 second. So here's the punchline. So the punchline says that you want to compute the quantum multiplication. Actually, we're just going to use quantum multiplication by divisors, so quantum multiplication by elements of H2. So you want to know how can you quantum multiply by an element of H2. And this conjecture tells you quantum multiplication by this divisor, people usually say divisor, they just mean element of H2, is the same as classical multiplication plus this quantum correction. The quantum correction has a h bar in front. What's h bar? It's the parameter of the C star equivariant parameter, so the generator of C star equivariant cohomology of a point. So this manifests the fact that if we were to get rid of the C star equivariant cohomology, well, that would be like setting this h bar to 0, and then all this stuff would go away, and we'd just be left with the classical multiplication. Okay, so h bar times a sum over the roots. So roots means just this special subset. There's a pairing between alpha and u, sorry. There's a pairing between alpha and u, which makes sense because alpha lives in h lower 2 and u lives in h upper 2. There's this factor, which I'll explain in 1 second, q alpha over 1 minus q alpha. And there's this operator, okay? So effectively, this big infinite sum of these 3-point Gromov-Witten invariants has been collapsed into a finite sum at the expense of introducing these special operators L alpha. And okay, now let me explain what's the other features here. So this is quantum multiplication, and I'll think of the quantum multiplication as depending on a parameter. And for me, q won't be a variable, it'll be a number. Well, not really a number. It'll be what? It'll be an element of h2 of y with coefficients in C star. Okay, so this is called I think the Kähler torus in the language of Okounkov. So this q will live in this Kähler torus, but not just anywhere in the Kähler torus, in what's called the regular part of the Kähler torus. So these alphas, they're elements of h lower 2 with coefficients in z. That means that they can be considered as weights of this h upper 2 with coefficients in C star. So alpha can be considered as a map from this h upper 2 of C star to C star. I write that map as q to the power alpha. So this regular part of this Kähler torus means those q's where q to the alpha is not 1 for all alpha. And so this quantum multiplication will be quantum multiplication by this element of h upper 2, but will depend on this parameter q, which lives in h upper 2 with coefficients in C star. And then this denominator here is well defined because I forced it to be well defined by only taking q's in this regular locus. Yeah?
What is the role of t? So for example, the parameters generating the t-equivariant homology of a point enters in this picture or not? I mean, because you have t, but at the end of the day it does not appear in the formula.
That's a good...
So why you switch on t? I mean, I can switch it on
You can switch it off. It doesn't make it doesn't play a huge role. I don't have a great answer to that question. I think it does not play a huge role in what follows.
So why did you plug in?
Why do you use it? We'll see later when we go to the representation theoretic meaning of this thing that it kind of plays a natural role. So, but it is true that you could just switch it off.
Do you have an explanation for the name Kähler-Roots?
Kähler-Roots. So Okunkov has this philosophy that symplectic resolutions of the Lie algebras of the 21st century. You might have heard this quote before. I think I probably said it more than Okunkov said it, because I say it all the time because I think it's entertaining. And so his idea is that the basic example of a symplectic resolution is cotangent bundle of the flag variety. And so that thing is kind of associated with the semi-simple Lie algebra, whose flag variety you wanted. And now if you take an arbitrary symplectic resolution, you should kind of think that that it's a generalization of a semi-simple Lie algebra. So as a generalization of a semi-simple Lie algebra, there should be a kind of root system. There should be a set of roots. In fact, Okunkov defined two sets of roots. This one called the Kähler roots, and another set called the equivariant roots. And under symplectic duality, they're swapped. So this is the one kind of roots that a symplectic resolution has. And why they're called Kähler, I guess because it has something to do with this usual use of the word Kähler in this subject. It has to do with kind of deformations and so on. Somebody else can answer that question. Yeah?
Why do you need quantum cohomology for this?
Well, this is a theorem about quantum cohomology, or conjecture rather, about quantum cohomology. It's just telling you how the quantum multiplication can be rewritten. So the left-hand side here, which I didn't define, is the operator of quantum multiplication. So quantum cohomology is in the left-hand side of this. And this is, maybe I should emphasize, this is an equality of operators on the cohomology. So quantum multiplication is it's an operator on the cohomology. Classical multiplication is also an operator on the cohomology. And these L alphas are some operators on the cohomology.
So you can effectively compute the no-returning invariants out of this problem.
Yeah. Yeah. So the goal of this Okunkov program, which I'll come to, is given a symplectic resolution, try to find this set of Kähler roots and try to find all these L alphas. And if you've done that, well, then you've understood the quantum cohomology, at least the quantum multiplication by divisors. But there's more to the conjecture. We'll come to it soon. Yeah? It's not necessarily generated. If it's generated by the degree 2 part, then you get everything, but it's not necessarily generated by the degree 2 part. For certain y's it will be, and for others it won't necessarily be. I don't know. Even when it's not, though, you can still somehow, well, okay, we'll come to that. It's a good question, and we'll come to it later. Okay, so next point. So I said that there's this operator, L alpha, but we actually have quite a bit of control over what kind of operator it is. It's not just some random thing operating in the cohomology. It comes via Steinberg correspondence. So let me explain that. So there's this thing called the Steinberg variety. So we had a symplectic resolution, y to x. And you can form the fiber product of y cross y over x. And in the case of the cotangent bundle of the flag variety, this is a classically studied thing called the Steinberg variety. And so for any symplectic resolution, people also call it the Steinberg variety of the symplectic resolution. And every symplectic resolution is semi-small. It's a theorem of Gaudin. And because it's semi-small, this Steinberg variety has the same dimension as the dimension of y. So the Steinberg variety has, so that's this equality here. So that's this semi-smallness of the symplectic resolution ensures the Steinberg variety is also of dimension d. And now I take the homology of the Steinberg variety, and again, via the general theory of symplectic resolutions, this thing, homology in the top degree of the Steinberg variety, is an algebra. In fact, in the sheaf theoretic language, it's the endomorphism algebra of the push forward of the constant sheaf. Maybe it's worth writing it. So if you, since we were talking about this last night, let me write it. A fundamental result is that this Steinberg, that this H2D of the Steinberg variety is the same as the endomorphisms of the push forward of the constant sheaf. So this constant sheaf on Y, because it's a semi-small map, the push forward will be a semi-simple perverse sheaf on X. We can take its endomorphisms. This is endomorphisms in the category of perverse sheaves. And this is a, I don't know, equality, I call it Chris Ginsburg equality, but it's like, not really due to them, but.
L alpha is proper with respect to one of the projections, right?
Sorry?
L alpha is proper with respect to one of the projections? Because you could define some operator, no?
Yeah. But you mean projection, you mean Y to X. Well, Y to X is proper.
Okay. Maybe you would just say, well, I will define the operator alpha.
Yeah, so okay, so let me just say. So this homology of the Steinberg variety acts on the cohomology of Y. Even, well, I'm writing without equivariance just for simplicity at the moment, but you could insert the equivariance. So this thing acts on the cohomology of Y by correspondences. And Y to X is proper, so there's no problem. And unfortunately, I mean, it would be particularly nice if this L alpha was, so this Steinberg variety, or this has some bunch of irreducible components, and their classes form a basis of this convolution algebra here. But this L alpha won't typically be the class of one of the irreducible components. It'll be just some element of this thing. Okay. So these L alphas, which are like the, in order to understand this formula, what's the missing ingredient, right? Everything is known, basically, except for this L alpha. So this missing ingredient, it's some element of this, some what they call Steinberg operator, some element in this homology of the Steinberg variety, which sort of needs to be determined. But still, it's of a geometric nature. So it's telling us that the quantum multiplication, the correction to the classical multiplication is given by this thing here, and this guy part here, the important piece of the right-hand side, is of a geometric nature. And we'll see in the examples that where it comes from. Okay, any questions? Now, yeah?
So just a comment on what you just spoke. Is it not important for T to be there so that you can define the movement?
For which to be there?
For T, for the existence of T.
What's D?
Towards T. Like
Oh, T. No, this.
define the movement invariants. Because these things are not proper, right? So then you need to do the
Yeah, because I was thinking about the stable envelope. So I know that because you have a projection for Steinberg variety to two copies of Y, then you put back, but then in the push forward you need some proper support for that alpha. Or at left, or right, as Frank is saying, that you need some equivalence in order to avoid proper support of the class.
In the definition of the quantum cohomology, you mean?
I'm just saying because these are not proper, so then we need to apply the localization.
Yeah, I think not, but I don't know for sure. That's okay. And there was a question about what happens for multiplication by higher elements in the cohomology. So this is all about multiplication by elements in H2. And as was pointed out, if we know that the cohomology is just generated by H2, well, we can define multiplication, quantum multiplication by other elements just by successive compositions. There's not going to be a exact formula like this for other quantum multiplications, but at the very least, part of this, I guess, our Konkoff conjecture is that that nonetheless, this quantum multiplication will be also well defined, like for this parameter. Okay, so those power series that could occur will be well defined at these values of Q, where Q is again in this regular part of this scalar torus. Okay. Okay, so this conjecture was was like been a lot of intensive work, like say over the last decade, by Kunkov and many of his students and collaborators. So here's not a non-complete list of some of the results. There's even more papers on this subject. So I guess the first paper on this, where they laid out this kind of program, was a paper that studied the cotangent bundle of the full flag variety of any for any semi-simple group. A paper of Dipartimento Kunkov from about 2010. That was followed by this very long paper book of Moliko Kunkov, where they studied this for quiver varieties. There was also work of McBreen and Schenfeld, where they again verified this conjecture for hypertoric varieties. Paper of Chanjiang Su studying cotangent bundle of Gmod P's for any semi-simple group. And finally, a paper of Danilenko verifying this conjecture for affine Grassmannian slices. And when I say verifying the conjecture, I mean they carried out this program. So they figured out what this set of Kähler roots are, and for each of these Kähler roots alpha, they found L alpha and proved that that formula, the main formula above, is true. Okay, so we're going to focus, I guess, on these two in this lectures. Any questions? Okay. So before I go on, I wanted to make one further kind of structural comment. So the quantum cohomology is one important feature of it is that it's a commutative ring. So if you take quantum multiplication by one element and quantum multiplication by another element, they'll commute as operators on the cohomology. So in this way, we can consider, for example, we can consider all possible quantum multiplications by every element of H2. So a set of all quantum multiplications by all elements of H2. And this will be a subspace of the endomorphisms of the cohomology. Okay, so and it will be not just any subspace, but what I call a commutative subspace. So a subspace of elements, all of which commute under each other. So stepping back, we can see that for every element in this regular part of this Kähler torus, Q, we can associate quantum multiplications at that parameter Q. And this will produce a commutative subspace. So using this quantum cohomology, we get a map from this H upper 2, with coefficients in C star, regular part. It's regular part of this Kähler torus. So to the set of all commutative subspaces. Later in this series, we're going to be interested in understanding what happens when we compactify this map. In other words, what's the closure of the image of this map? So that's sort of the preview of where we're going. And similarly, we could do the same thing, not just with multiplication by H2, but multiplication by all elements of the cohomology. And then we get a map to the space of commutative subalgebras of the endomorphisms of the cohomology. From this viewpoint, one way to understand quantum cohomology could be find some algebra which is going to act on the cohomology, and then identify the quantum cohomology as coming from a certain subspace or subalgebra of that algebra. Okay. Maybe this is a little too vague for now, but we'll see what this means soon. Okay, any questions? Okay, so now we go on to looking at the quantum cohomology of these quiver varieties. So I wrote ADE quiver varieties, so those quiver varieties coming from ADE linking diagrams. So those, actually, so I'm simplifying things a lot by going to this ADE linking diagram. So actually, a lot of the interesting stuff is thrown away by looking at the ADE linking diagrams. But maybe we'll, perhaps in Olivier's lectures next week, we'll see a little bit of the traces of what happens outside of the ADE case. Well, I won't be here next week, so. Okay, so let's just return to our setup. We take a semi-simple, simply based Lie algebra. Lambda and mu are dominant weights. I'm going to blur the distinction between weights and co-weights. I did what I said before. using it to form this quiver gauge theory, and I form my quiver variety. Okay, so in order to formulate this theorem, like to formulate how Nakajima's conjecture works for this ADE dekinograms, we need a bit of this geometric representation theory. So this is by now kind of classical results. So let me start. So one reason why Nakajima introduced quiver varieties was because he wanted to give actions of these semi-simple Lie algebras geometrically. So here's the theorem, is that there's an action of this Lie algebra G on the direct sum of the cohomologies of these Nakajima quiver varieties. So I have to take the direct sum over mu. So remember, lambda determines the framing. So I keep the framing fixed, and by taking the direct sum over mu, I change all possible gauge vertices, and such that the cohomology of this m lambda mu is isomorphic to a mu weight space. And moreover, the action of this semi-simple Lie algebra on the cohomology of the quiver variety is by correspondences. So Nakajima introduced these special correspondences between quiver varieties so that they would give an action of G. Another way of phrasing it is that you could say that there's a map, and this is already in Nakajima's work, there's a map from the universal enveloping algebra to this kind of Steinberg algebra, so the topomology of the Steinberg variety. But the action of this G will change the mu, right? Because this mu is a weight space for G. So when you act by some generators, EI, FI of G, it'll change weight spaces. So for that reason, to make this precise, we have to not just work with a single quiver variety, but rather take this kind of disjoint union over all mu's. And then it's somehow important that that we have those upstairs, we take the disjoint union, but downstairs, for those affine varieties, they actually sit one inside the other, so that we can make sense of what it means to form correspondences between the different quiver varieties. Okay, so this is I want to explain this action. It's going to be kind of a black box, which we're going to use later. This is like, I don't know, from 30 years ago, maybe now, I guess, this theorem. And it built on earlier work of Ginsburg, who studied the case of cotangent bundles of partial flag varieties. Okay. So this action was generalized, well, maybe generalized by many, many people in different ways. But one way very soon after that it was generalized was by Varignolo. And there's a bigger algebra. So this G, or its universal enveloping algebra, there's a bigger algebra called the Yangian of G. And again, I won't get into its definition. But this action of the G can be extended to an action of this Yangian. And it explains some features. For example, a little bit explains what's going on with this equivariant parameters. So this Yangian of G also acts on this cohomology, now equivariant cohomology of the quiver variety, and such that, well, after specializing the equivariant parameters, let's say, we get a tensor product of fundamental modules for this Yangian. So fundamental modules for a Yangian are indexed by kind of two parameters, one which is this fundamental weight of G, and the second parameter is called the spectral parameter, which is the complex number in this case. Yeah.
Here as well you could turn off T, no? Because the Yangian in this case is always depending on the H bar, am I right? So they won't.
Yeah. So as I said, the T is influencing here and here, so it becomes these spectral parameters for the. Okay. So this is the theorem of Varignolo. And in the brief comment, in the non-ADE case, the more general quivers, this is generalized by, I guess, what theory of this cohomological Hall algebras and stuff, which Olivier will talk about next week. Okay. How are we doing on time? We have like 3 minutes left. Well, 5 minutes, yeah, because I started a little late. Okay, so maybe we'll just get to the main theorem here. So To talk about quantum cohomology, remember in the statement there's a lot of stuff about H2. So we better understand H2 of our quiver variety well. So where does the H2 come from? Well, H2 usually comes from line bundles. Where do line bundles come from? Well, we have these tautological vector bundles on the quiver variety. Because the quiver variety was defined by quotienting by an action of these GLs, we end up with these tautological vector bundles. In the example where it's a partial fact variety, those are just the usual tautological vector bundles on a partial fact variety or cotangent bundle. So from these tautological vector bundles, we can form line bundles. From these line bundles, we can form classes in H2. Sorry, I should have said C1 here, I suppose. We can form classes in H2. And so for each I, so here I is an element of capital I, which is the vertices of our quiver. So for each vertex of our quiver, we get a line bundle. And therefore, if we have Z to the set of vertices, we get a map to this H2 with coefficients in Z. And this map will usually be an isomorphism. I think it will be an isomorphism as long as all of these VIs are non-zero. Otherwise, it'll be surjective, but not injective. And let's just assume that it's an isomorphism. And using that, we're going to identify this H upper 2, well, with coefficients in C star, with, I'll write little h, that's the Cartan subalgebra of G. So I don't write T because I'm trying to keep T for the torus, which is acting on the quiver variety, not to be confused with this torus. So I have the H upper 2 with coefficient C is the Cartan subalgebra, H lower 2 with coefficient C is going to be the dual of the Cartan subalgebra, and capital H will be this Kähler torus, which will be the H2 with coefficients in C star. And now we can state the theorem of Malikov-Kunkov. So under this identifications that I have here, delta plus, why does it say usually? Delta plus will be identified with a set of usual positive roots of G. So where do positive roots live? They live inside of the dual of the Lie algebra, the dual of the Cartan subalgebra. So that's good. So the positive roots live in here. So it makes sense. And delta plus is supposed to live in here, well, with coefficients in Z. So it makes sense to identify them. So under this identification star, this delta plus becomes the usual positive roots of G. That means this regular part of the Kähler torus becomes, well, just the usual regular part of the torus. So like the set of all elements in the torus where all of the positive roots don't take value 1. And moreover, we have this standard Okoukhov formula for quantum multiplication. So quantum multiplication equals classical multiplication plus this correction term. And I've told you that this alphas are the actual usual positive roots of G. So all I need to do is tell you what L alpha is. And here's the answer. This L alpha comes from the action of G on the quiver variety. So remember we had G acting on the cohomology of the, cohomology of the quiver variety. We had the Lie algebra acting on the cohomology of the quiver variety, Nakajima's theorem. And there's special elements in the Lie algebra called the E alpha and F alpha, those root vectors. And this L alpha will be given by this combination of E alpha F alpha plus F alpha E alpha. The reason why you sort of like would expect something like this is you actually, right, you have to get back to where the E alpha will change you from one quiver variety to another quiver variety. It will change the mu. But E alpha F alpha will take you there and then take you back. So this makes sense? This thing is actually an operator on the cohomology of a single quiver variety. So this is like great theorem because this L alpha, which could have been just some like arbitrary operator on the cohomology quiver variety, well, it couldn't have been arbitrary because it was supposed to come from the Steinberg, but comes from this very special element of the Lie algebra. So, okay, I'll just stop then. So yeah, okay, let me stop after this. So just in case you're not familiar, what are these E alpha, F alpha guys like? So for example, if G is SLM, what are the positive roots? The positive roots of SLM are where you usually write epsilon I minus epsilon j. In other words, you put a 1 in the position I and a minus 1 in position j, a bunch of zeros. And the corresponding root vector E alpha is a matrix where you have a 1 in one spot, namely in the ith row and jth column. And there's an analog of these elements for any semi-simple Lie algebra. Okay, I'll stop there.